All right, my name is Lucas Brockman,
And I'm Leah Brown.
and we developed probabilistic human risk analysis. So basically, what this does is it takes PRAs, uncoupled failure flow analysis, things of that nature, and combines them into a new risk analysis method that focuses on human injury instead of focusing on the mechanical system itself and what it would cost to fix that.
And this method of risk assessment is mostly useful for systems in which human injury is far more expensive than the equipment involved in the system.
Like for example, at my job at Medtronic, a lot of the systems that I work on are, while they're expensive, the cost of a human injury would far exceed any cost of any safety system. So those would be a very good use for those.
And looking at my complex system that I reviewed throughout the semester, the biosafety level 4 laboratory, essentially human injury causes a complete failure of the system. So human injury becomes far more important than any of the machinery or equipment within the lab.
Also, or similarly, the lathe subsystem that I've been working on for the majority of the semester, um, lathes are relatively cheap, and the cost of a human injuring themselves on it could be extremely high. So that is what we decided to choose for this um, paper. So we developed a flowchart for how to accomplish this risk assessment. First, you have to calculate the probability of the failure occurring. So this would be the PRAs, the uncoupled failure flows, that kind of stuff. Then next, you have to multiply the probability of it occurring by the probability of human interaction. So this would take into account any safety interlocks that you have to put in, physical barriers, exposure time to the failure, things of that nature. And then the product of those two get multiplied into the probability of human injury, assuming the interaction took place. So it would be force involved, the likelihood of infection, things like that. And then those three are, or the product of those three are multiplied by the estimated cost of the injury. So that would take into account statistical value of human life, legal costs, medical insurance costs, and downtime and loss of production. And finally, the product of all those four gets multiplied by the morality coefficient. So this is basically a coefficient that the company or designer would have to determine before the design is actually complete. This is basically how many more times are you willing to pay for the safety system than you would statistically be saving. So with a morality coefficient of 2, you would be willing to pay twice as much for safety equipment than you would be potentially saving with it. So for the lathe subsystem, we identified 3 major safety interlocks that could potentially prevent humans from coming to harm. The first is a shield around the work area. This would prevent any of the material from coming out of the system. Say if the tool breaks or a part gets released from the chuck, it would prevent that from interacting with the human. Next would be rubberized handles to prevent electrical shock to the operator. And finally, light curtains that would detect if a operator reached into the work area and that would shut down the machinery to prevent any potential injuries from occurring. So each of these we assigned a probability of incidents occurring. And this is taken into account over the lifespan of the machine. So with the lathe, this would be a large projectile would leave the area 1 out of every 4 lathes. electrical shock 0.05, and operator caught in the mechanisms, that would be 0.5, because that's a very common occurrence. Probability of human interaction, this is with and without the safety features being put into place. This allows us to have a control system to analyze against. The probability of injury, that's the same between each of these. That's assuming that for example, with the shield around the work area, that the part has already left the system, and what's the probability that the human will be injured by it. And then next, the estimated cost of the injury. So for the large projectile leaves the work area, we sign that $50,000 medical bill. We base that off of a family member who had a severe laceration that could have happened on the lathe. For the electrical shock, $1,250, basically an ER visit plus maybe a couple of follow-ups. The operator cut mechanisms, that's probably just stitches, so basic ER visit, $1,000. So from these, we can get the estimated costs. So with the shield around the area, or around the work area, we get an estimated cost of $281 versus $5,625 without the shield. Similarly, the rubberized handle, 94 cents with, $90 without. Each of these are the instance with the safety system is subtracted from the instance without it, and the cost savings can then be generated.
Finally, looking at the results of this analysis with respect to cost to the owners, essentially looking at you want to compare the cost of the safety equipment with the cost savings calculated in Table 1. For the shield around the work area, the cost savings are $5,000 and the cost of safety equipment is $1,000. Given that our morality constant in this case was 3, meaning that they're willing to pay 3 times as much as would be saved, then the shield should definitely be applied. It passes through this analysis. The rubberized handles pass as well because the equipment only costs $50 and the savings are $88. But then the light curtain is $2,000 for installation, but only saves $675 over the lifetime of the lathe, so it's not worth it based on this method of analysis.
So this method of analysis would be extremely useful to engineers of many different trades and many different fields of study and work, and we hope that you give it consideration and hopefully utilize it in the future. Thanks for listening. Have a good evening.